core analysis. It's kind of an underrated thing nowadays. I work for the Intel Corporation, and so most of my examples will be done in x86, but you can actually use this on ARM and other architectures as well. All right, so if you guys want to follow along, you can use your laptop, your Linux laptop, and you'll need a couple of tools. Bin utilities with object dump, readelf, and nm, GDB, and GCC. I'll be going through all these examples live, so if you don't have a laptop, then you can follow along. And the presentation is located here at this Google address, so you can download it in PDF format. It's goo.gl, and then capital, and then slash capital O, and then lowercase CYRK. Okay, so what is a core? Core is basically an archaic name for memory. Basically, back in the old days, magnetic core memory was an early form of random access memory. And the term core comes from the convention that transformers, basically conventional transformers with windings surrounding the magnetic core. And nowadays, of course, a magnetic core memory is superseded by semiconductor memory. And it's not really to be mixed up with the new term core, which is for like processors. So if you have multi-core system, we're talking about processors. But back in the old days, cores really meant memory. And what's a core dump? Basically, a core dump is the recorded state of working memory of a process image. Process state is also stored in there. And it's stored in a binary format. In Linux, it's typically stored in ELF. Back in the old days, it was stored in A.out. And in Mac OS X, you can get core dumps in Macho format. Well, why should you care? Well, core dumps are cross-architecture and cross-platform. So you can actually use these on other operating systems as well. So just like I said, Mac OS X is an example. AIX you can use core dumps in, HPUX, and other systems. So if you learn how to use core dump on one system, you can actually take those techniques and use them to debug other systems as well. Core dumps are really good for getting post-mortem information from customers. So for instance, if you're designing a cell phone system, and all of a sudden your cell phone crashes, or an application on your cell phone crashes, you can generate a core dump and it can send that over the air to you as a developer, and you can use that to debug your information. So it's a good way for open source software developers to get post-mortem information from users. Also, it's pretty hardcore. So like if you actually learn how to do this, you'll learn a lot about how applications work internally. How do you trigger a core dump? Well, basically, the easiest way to trigger a core dump on a terminal is there's a quick character that you can send, and it will generate a core dump. Another way you can do it is via the kill signal. So if your application is acting a little wonky, you can actually send a signal to the application and do a core dump. Any erroneous behavior which triggers a dumpable signal. So for instance, illegal instruction, segmentation violation, the abort signal, those will all create core dumps. Now, typically in your distribution, core dumps are disabled because you can imagine if you have a large Oracle database, for instance, with gigs of memory, and you create a core dump, it's going to take a long time to quit, and it's going to store a really large file, and you may not want that. So by default, they're disabled, and so to enable core dump, you're going to need to configure proper resource limits. So basically, there's a resource limit for core dumps, and resource limits are kind of funky, so I'll kind of explain it. So a hard limit can only be increased by root, but a hard limit can be decreased per process by any user. The soft limit kind of maps to a hard limit, so you can't grow your soft limit larger than a hard limit, but the soft limit can go positive or negative, and it's limited, and it can be used by any user. And the command in your shell that will actually maintain resource limits or manage resource limits is ulimit if you're using shell or bash. If you can configure, basically the parameters to configure soft limit is located in the bottom here. So you can basically say, I want my core dump to be as big as possible. So, or you could say a core dump can utilize as much memory as is available. And you can specify that by ulimit -s-c unlimited. Or you can constrain that by a set of kilobytes. So you can say ulimit -s-c, and then you specify the size of kilobytes. So I can generate a core pretty easily. So I'm going to go through that example right now. So basically the gist of it is you run an application and you can send a quick character, which is control \, and it will generate a core. But first you need to set the resource limit. So let me show you that over here. So if I do, so first I have to set the resource limit. So I do ulimit -c unlimited, and that's why that's. And then I could run my command. It's an arbitrary command. I'll just run sleep. I'll just sleep there. And basically, actually, I should run that in the program. So actually, if I hit the control \, it's going to quit, and then it's going to give me a core dump. And that core dump's basically, if I search for it, I'm going to get that core file right here. So let's say core. And that file right now is basically ELF 32-bit. I don't know if you guys can see that. Let me move this window a little bit.
That's good.
Okay. So it's a 32-bit ELF file, and it tells you exactly what the command and the parameters are for what was run. You can also generate a core dump programmatically. So let's say you have a certain condition in your code that you know you should never hit, but you want to generate a core dump to debug it. You can use what they call the abort instruction. So I put some code up here on my website. If you guys want to download it, you can go to that 1T SGZ Google site, and I'll have the source code for this sample that I'm going to show you guys. So basically, this uses two functions to at least initialize the resource constraints. So first one is getRlimit, which basically gets the resource limits on the hard limits, basically set by root, and setRlimit actually allows you to set the soft limits. And it takes in a parameter. It takes in the parameter an ID basically to say what resource you want to manipulate. In this particular case, I'm going to manipulate rlimit for core. So it's going to be rlimit_core is what we're going to use. And you pass in basically a structure that defines basically the hard and the soft limits that you want to specify. So I'll give you let's see. So let me pull that out. And I'll show you the guys' code. There you go. So basically, it creates a structure rlimit, initializes it to 0.
Can you move your window over just a touch more?
Okay. I don't know what's going on with this thing. It's flipping my.
More.
Is that good? No. Okay. How's that?
Not yet.
All right, come on. Running out of space.
There we go.
Good. All right, here we go. So, yeah, follow my cursor along here. So it's gonna, this function right here is gonna get the resource limits for the system. And it's going to check if your hard limit, which is specified under the member variable rlim max, is less than a megabyte. And basically, I just said that just check to make sure that you can actually generate a legitimate core node. And then what it's going to do is it's going to set the soft limit, which is specified under the rlim_cur, to rlim max. So it's going to basically give you the biggest core node possible. Up to the biggest core, size possible. And it's going to set that limit by sending that back as a syscall to the kernel. And then it's going to just abort, which is over here, which will have the process get a signal, sig abort, which will then cause a core node. So
If the node is too small, do you get no info or partial info?
yeah, partial.
I've never seen a partial core node. It's either all or nothing.
You sure? Okay. So we can try that actually. So yeah, I've actually always used unlimited or something like that. So okay. So basically, this is an example of simple abort, which will. So actually, let me set the limits back. You limit. So that's the default. And if I run simple abort, it's going to grow the size. So right now it says the soft limit is 0, but the hard limit is basically 4 gigs. And now it sets the soft limit to 4 gigs and the hard limit. And then it doesn't abort and it don't store. Now the core file here in particular is pretty small. So it's about 155 kilobytes. So let's take a look and see, what if I set the, actually I have to modify the code a little bit. So let me set the code to 10 kilobytes. So I'll set the R limit to 10 kilobytes. And then I'll just generate the code. And then I'll run simple work. Let's see. Okay, so you're correct. Basically, if you make the core node size too small, you won't get a core node at all. So sorry, I was wrong about that. Let's see. So what's next? Okay. So this is I don't know if you guys can see this very well, but this is a typical layout of user space memory under Linux in a 32-bit environment. So basically at the top you have kernel space from all F's down to C and then all zeros. And then after that you have the stack. And the stack grows downwards. And then you have your shared libraries, your VDSO, and your shared memory. And then you have the heap that grows upwards. And then you have the uninitialized data section, which is also called the VSS, which I think it says this block starts at a symbol or something like that section. And then you have initialized data and text. So basically, your initialized data is all your constants or all the initial variables that you set. Uninitialized data sections are like static variables and so forth. Those are all initialized to 0. And your shared libraries and so forth are up here. Okay, you can actually examine the maps that you get once you run all the memory maps that you have once you run your program using proc. So you basically say cat proc the process ID and maps, and it'll show you basically your libraries where they're mapped to in memory, the VDSO, your heap and your stack, and also show you your application data as well. So I can show you an example of that as well. That was a solid example that I'll show you. So if I do cat proc 1655 and then maps, unfortunately I don't have enough space. Let me shrink that down a little bit. I'll show you all the things that are mapped in, and then the associated files with it, and so forth. Can you guys see that? There's also another interesting thing to see with memory maps is address space layout randomization. So as a security precaution, the Linux kernel can randomize the base address of the stack, the libraries, the heap, and also the VDSO. So currently I have that enabled right now. So if I were to run this, if I were to run sleep again, let me kill the one I was running already, and then run it again, and then cat the mask for that, you'll notice that the addresses for instance, like the VDSO address is over here, and when it gets called again, called in a separate process, it has a different address, starting address for the VDSO. So, and that's controllable by Linux via this proc sys kernel randomized VA page. Some old applications have issues with with moving certain things, so you can actually disable ASLR if you needed to. And basically, I just showed you the two diffs between the two maps. Okay, so basically, ELF files represent executable, relocatable, or shared object files. You can represent other things as well, but typically these are the files that you're going to manipulate in ELF format. ELF stands for executable and linkable format, and one part of ELF, which is interesting, is it has an interpreter. So the interpreter will manage dynamic linking. So the interpreter, or I'll call it the loader, or library loader, is represented as ld.so or ld-linux.so. And the C library, as everybody knows, is libc.so. And the contents of an ELF file, basically, there's two major parts to an ELF file. You have, well, three major parts. You have the actual ELF header that has information about where two other components are, the program and the section headers. The program headers provide maps for segments in an executable or an object file or a library file or a shared object file. And the section headers points to, basically it points to segments, but it points to locations within segments, and I'll show you a diagram of that to make it more clear. Segments are basically chunks of memory which are used to build a process image. And sections provide information for linking your relocation. So I'll give you an example of that. So here's a typical ELF file. A typical ELF file will have an ELF header, a program header table, a text section, read-only data section, and a data section. And this, basically, the program headers point to chunks of data, and the section headers point to locations within the different sections. So here's an example of typical ELF header. So basically, at the beginning, there's some magic data that tells you that it's an ELF file. It tells you if it's a 32-bit Intel 32-bit machine or 64-bit machine. It tells you the entry point address, where the start section is, or the start code is. It tells you the size of the program headers and the size of the section headers, and so forth. So to get this information from your program, a very nice program to get that is readelf. So I'll demonstrate that right now. So readelf, if I wanted to run readelf on the file, if you do readelf-a, it will dump all the ELF information that it can from your ELF file. So in this particular case, it shows the header, and then it shows some information about the sections and the program headers. So in the core down, there are some really interesting program headers. One is the load program header, which basically maps. Basically, the load segment will basically map code or data to a specific address. And the node segment will have special information that somebody wants to parse. So for instance, if the kernel gives you a core down, it will drop some interesting information like the register status, what signal that caused a core down, and so forth. It'll dump that in the node segment. And if you wanted to get the actual memory maps that I showed you in when I did the cat, procs, and PID maps, they'll be represented by these load segments. So each of these loads are basically memory map ranges. In executables, there's also a dynamic section, and there's other sections, or segments, rather. Some useful segments are, as I showed a little bit before, the text section, which has a program code, the data section that has initialized local variables, BSS, which has statically allocated variables, RO data, which has constants and immutable strings, dotted int infini, which has start and end code. The PLT, which we'll get into a little bit later, is a procedure linkage table, which is for dynamic linking. And the dot, which is for data, dynamic data that you get in the dynamic library. And the syntax has a symbol table. So when you run nm, it's going to take a look at the syntax section and get you information about all the symbols in your L file. Okay. So let me do a readelf on a core file, and we'll take a look at that. So if I do a readelf A on a core file, let me grow this window a little bit. Okay, so this is a core file that was generated. On the very top, it's going to have a note header, which is going to have information that's described at the bottom here. It's the first data that's going to have in the notes is going to be this PR status structure. The PR status structure has information like what signal killed the process, what pending signals there are, what's the registers, and so forth. And the PRPS info is going to have some information about the actual application, like the application name and the user ID, the group ID, and so forth. The auxiliary vector is going to have some interesting information about the application. I'll go into that a little bit later. And then also the kernel may opt to add some additional information. So for instance, in the 386, in the 32-bit architectures for Intel, or 64-bit, is going to drop information, this Linux note. And the Linux note is going to have information like floating point registers and so forth. Okay, so anybody have any questions or anything? All right. So let's say I wanted to manually take a core file and I wanted to find out exactly where a function was located. One way you can do that is you have to first you need the original executable, and so that you can find the symbol that you're looking for. So for instance, in this example, we're going to take a look at this main function, and we're going to find out where that's located in the core file. So an executable file, you take a look at you do readelf, and you take a look at the syntax section, and it's going to show you the main function. And then what you can do is you can take the core file that was generated after the core dump, and you can map the address. In this particular case, it's 454, and you can map it to one of the load segments. And what this will show you, and I'm sorry, it's a little bit negative here, but what this will show you is like offset located within the core file, and then the base address of the memory map. So for instance, if I wanted to get this particular address, what I would do is I would subtract this from this, and then I'd get an offset, and then I'd add it by the offset within the core file, and then I can get the actual data. So in this particular case, will be code. So this is what the slide is explaining here. And then one thing you have to keep in mind is that the core dump might not have all the data. It might not have all the executable data code or whatever, because there may be some dynamic paging involved, where the system will only get as much information as it needs. It'll lazy load information as opposed to loading everything beforehand. So let's see. Let's see if I can show a good example of this. Let's see. So I can do an object dump. I'm sorry. I can do a readout. Minus A on I want this example here, and I'm looking in the symbol table for the main function. So
Down at the bottom.
yeah, let's see. Let me make sure I run this. So example is basically a copy of simple Word, and it's going to generate a core dump that we're going to extend. So let's see. Okay, here we go. So I'm looking at a simple table, and just like the guy said, that main, it gives me this address here, 8048618. But if I look at the corresponding core file, and then I do a read off on that, then it's going to give me all of these mapped segments. And what you need to do is you need to basically find the virtual address range that has the code that you want. So let's see. See if I can remember that address.
Surely someone's written a program to use.
Yeah, I know. I'm just showing how the terminals are working. Yes, definitely no GDB is the program to do it. But I'm just showing for people who may want to see how this stuff is actually represented internally. Just go a little deeper into it. But anyway, okay, so I'll move a little bit further. If you trust me, basically we subtract that value from the base address on the core file, and then you add it by the offset, you're going to get the code data from me. So let me move a little bit ahead here. Here's some information that maybe is not that easy to get from GDB. If you wanted to actually take a look at the PR status, GDB will give you some details of PR status, but it doesn't give you everything. And if you wanted to map that information yourself, I've come up with a very easy technique to do it. And if somebody knows an easier way, they can interrupt me and tell me, but this is kind of a little bit more complicated way that I've come up with. And basically, the way this works is I'm going to leverage the debugger GDB, but I'm going to leverage it to basically take a core dump and memory map it into into an executable space, and using GDB, I can take the PR status structure and PRPS info structure, and I can map it to the address that I want to get the actual details of PR status. You can write another program to do this, but GDB actually is really nice to use in this particular case because it can take the dwarf information and it can allow you to do like casting of variables and so forth. You can cast the memory address to a structure and it'll dump out the actual details of the structure, and it's very nice to do, rather than manually writing this yourself. So in this particular example, I'm going to run GDB, and I'm going to take, I'm kind of getting ahead of myself here, but since everybody knows about GDB, I'll take GDB and I'll take this program cast expression, which is represented by that file there. And then what I'll do is I'll run it, and the first parameter it's going to take is a core file, and the second parameter it's going to take is the size. Basically, you can take the size. In this particular case, I'll take 4,096 bytes of the core. That's all I need for this particular example. Oh, sorry, I've got one more thing. I need to break at a certain location. So if I do a list, I'm going to break right before. Sorry, I'm going to break right before it returns back. So if I run that, it's going to break right there. And what it's doing is it's mapping the core file into the virtual memory of this application. And then given that address, I can actually cast an address which has the information that I want, which in this particular case is PR status and PRPS info. And I can cast that information to get the actual, I want to extract the data that I want. So I already did the offsets. I already calculated the offsets myself. So you basically do, so I know that because I told Memap to map it to 7777000, I know that I can look into the core file at a specific offset, and the offset's given to you by readout. I can take that offset and I can cast the structure. So let me show you that. So just using print, I can take, give you like star, which says give me the contents of the struct that I want. In this case, it's elf PR status, and then the address that I want. So in this case, it's 248. And if you look at the bottom here, it's a little hard to see, I'm sorry. But what it says is, in this particular case, you've got this signal number. It tells you the PI process IDs, and let's see, some timing information about how long the program's been running, I think, and then register data. Unfortunately, the register data is in decimal, and so that's not very helpful, but at least you can get some information about, if you just give them the core, you can get some information about how the signal that killed it or something like that.
Can you do that with just GDB with your helper?
You could, well, so let me show you GDB and what GDB will give you. So I'm not sure. So, but what I do know is if I just do, if I just take the example, I think it was a simple board and then core. GDB will tell you some basic information. It'll say that it terminated with signal 6. But it may not give you all the details you want. I haven't found a way, but if anybody knows of a way through GDB to actually fetch that information, it'd be very helpful. So going back to my example. I'll just dump out the PR PRPS info structure.
You need me to start there?
Oh, yes, thank you.
And how did you calculate those offsets?
I'll show you. It's not too bad. Okay, so let me move that. Unfortunately, I have no problem. Okay, so in this particular case, it tells you the process state. So, so with the PRS name, it'll tell you that process was, before it was interrupted by a signal, it was in a running state. That'll tell you the nice, I think this is the niceness value here. I'll tell you the user ID, the group ID. So in this particular case, it's my first user, which is 1000 Mark P, I guess. The group ID is users. It will tell you the name of the program that you're running, and it will tell you the arguments that you passed as well. So you can use that to fetch the PRPS info structure. I haven't figured out a way to do that through GDB yet, but it might be. The other thing that you can get is the auxiliary vector, but GDB allows you to get that pretty easily. So if you just do, so you take your core file and your executable file, and you do info, I think it's auxv, that'll give you the auxiliary vector. And that gives you, say, like the entry point, where the program headers are located, the base address of the interpreter, the entry point of the program, the user ID, the group ID, and the name. So actually, the auxiliary vector actually kind of maps some of the information that's in PRPS info as well. It'll tell you the architecture that this program is running on. So for instance, if you have a program running on multiple architectures, it might be useful to get the auxiliary vector to find out details about the system. Also tells you page size, and so forth. So sometimes when you get bug reports, they don't tell you anything about the system that the program is running on. And the auxiliary vector gives you a lot of detailed information. So how did I calculate those values? It's an interesting way you can do it. So basically, every note is named. So there's a note that's named core, and there's a note that's named Linux. So if you just do a hex, if you do a hex edit on core, then let's see. If you look for capital CORE, that will give you some information about where to start. So basically, it's an 8-byte name. So it's like CORE, and then there's like zeros after it. So 0, 0, 0, 0, 0, and then that's the beginning of one of the structures. So basically, in that case, I got 248 for this particular case. And if you look again, there's another core, and then it followed by four zeros, and then that's the starting point for the next one. And the way to find out which is which, there's some header information up here too that tells you exactly what that represents, if it's PRPS info and so forth. But the easiest way to do it is in order. So the easiest way to do it, if I can get out of this program. The easiest way is just do a readelf. And then if you follow the order, this one, and that one, then let me shift that over. This one, and that one. You see there's 3 cores, and then there's one called Linux, and you can search for Linux as well. And I'll give you the starting point for all these structures. So, any questions before I get into something more? I get into the dynamic linking part. It's a little complicated. So, ELF handles dynamic linking via the PLT, which is unfortunately I kind of clipped it a little bit, it's the procedure linkage table. And PLT is basically a jump table for shared library functions. So when you start up your application, it doesn't really know where the libraries are going to be located, or where it's going to be mapped. The interpreter will, or like LDSO or LD Linux will actually map those things dynamically as you call the function. So the PLT is a fixed location within your binary that points to which basically says, okay, I need to go to a specific address, but I don't know where that address might be. So that address is going to be specified in data, and it's going to be manipulated by the interpreter. And this jump table gets initially, the jump table gets initialized to the interpreter. And when you call the function, whatever function that's dynamically linked, it will jump to the interpreter. The interpreter will say, okay, you jumped from this location. I know exactly what you need to be mapped to, and it's going to set that address, and then it's going to jump to the location where you need it. So the rel PLT is the actual destination address that the interpreter sets to where you're going to dynamically load to. This technique is called lazy loading. You don't want the dynamic linker to set up all the addresses initially, because that'll make the program take a long time to initialize. So you do it, as you need it. Which also means that not all dynamically linked functions will be mapped, which might be okay. But in the core dump, that means that when you actually when you get a core dump, if your function wasn't called, it won't be mapped. See this, but an example of this will be like the abort function in my simple abort program. So basically, it tells you that the PLT is located at a fixed address here. And if you take a look at a core file and you wanted to find out exactly where that function is in memory, then what you would do is assume you were given an address that you were interested in finding out where that was mapped dynamically. You map that. You basically take this function. You take this address and you map it with the core offset. And then the value at that offset is going to be the location of where, in the rel PLT, will be the location where that function is located. And you take that function, you take that virtual address, and this is how GDB will generate that virtual address for you. I can show you guys an example of it, but I'll move on.
If you want a specific command inside a function.
Right.
If you crash, even a kernel crash, a kernel crash, and you have what you have. If you use kdump or whatever, what you have is an address, and you want to go to the specific address and see where it is in the kernel. Although you can use the DBG, the kernel debug, but if you don't have a debug.
Right.
How can you do that?
So it's a little different for kernels because this is user space in particular. So there's the dynamic linking, but in the kernel, you can look at the system.map, and it'll tell you the exact address where the function is located.
But that's the function locator. I want something within the function.
You want to look
What offset within the function?
Right.
The only way I know to do this is by disassembly inside the GDB.
Right.
Take the VM Linux, do GDB on the VM Linux, and do disassembly. That's what I do, but is there another way?
GDB is probably the easiest way.
No, on the VM Linux. You could do GDB on the VM Linux if you have the VM Linux of the specific, and and you go to the specific address and see what
Oh, you want to see the source?
what code is specified for the
Yeah,
specific
yeah, you can do
address.
that. So you can do object dump minus s on VM Linux, and it will tell you, it will map the source code of the kernel to the actual to the actual location that you need to see. So I'll give you an example of object dump minus s. Just it's not VM Linux, unfortunately. I don't
Okay,
have
it's a
kernel crash, but this works the same way. So if you do object dump minus s, and in this particular case, I'm going to use simple abort. Oh, sorry, wrong file.
Go on object.
Okay, let's see.
Address the line is a lot easier.
It rarely works.
Sometimes, yeah.
What's so I was just going to show that when you do high-cast, let me move that window over, sorry. So it'll take the assembly code and then also the virtual address, and it'll map it to the code. And you do that with VMware as well. So that's how typically I would debug kernel dumps. So that's very useful. Sometimes it gets out of hand. So who was saying something about address to
Address the line.
Okay.
I just
So if you go back to your command prompt,
Okay.
address the line. There's ADDR2 line minus E minus F. The file. The addressing will get.
Okay, so what I was picking for random here. Do I have to do it like 0x?
No.
No, just like that. Oh, file will be the what? Say no such file.
Should be executed.
That's pretty weird.
No. E.
Oh, it's E is a file. Oh, interesting. Okay, well, it's showing me something here. It's saying that simple word :20.
So if you give minus F for the E, it'll give you the function.
And that works for VM Linux as well?
Yeah.
Okay. So
Okay.
that's a simple way to do it. Sometimes, yeah, I guess that'll work. All right.
ما في شيء مثلا كبير بكره
Um,
ما تصير كذا قدام.
See if there's anything else. You can tune your kernels in user space. So you could say that you could tell the kernel what kind of output you want in your kernel. So by default, it just basically dumps file-backed shared mappings. So for instance, if you have like libraries or your executable, anything that's mapped by file will dump that. But let's say you wanted to dump anonymous private mappings, or or private mappings. You can specify that as well, and that might be useful, but it'll increase the size of your kernels. You can also tell it what kind of file name to generate. So you can say by using this core pattern, you can specify. You can say like, let's say you get a core dump and you wanted the process ID. You can give it a pattern which will allow it to give you the process ID. You can also specify to have a core dump be piped into another program. So for instance, if you're working in a server and all of a sudden your application crashes, but you want that to automatically be emailed to another user, you can use core pattern to redirect the output of the core dump to a file, and then have that emailed automatically. So if you notice, sometimes in your Groovy environment, your application crashes, and then all of a sudden it says, "Okay, I detected that your application crashed," and then so forth. It is most likely using core pattern to detect when that happens and send an IPC. So you can also do live core dumps using this program called Gcore. It's actually a script that uses GDB. Let me generate an example. So I'll take my simple board program, and I'll just make it, instead of boarding, I'll just do a if node. So it's not aborting, it's still running. So if I do PS, it's PS. It's still there, it's not gone. And if I run gcore, and then, I think it's just a process ID, it will generate a core dump without killing the program. So let's say you wanted to examine the contents of your program while it's running. Let's say your program's not running correctly and you're not, you didn't initialize it, you're not in the GDB section or whatever, you just wanted to get a snapshot of that, of all the memory in your program, you could use gcore to do that. So that's a useful debug tool. And I think that's about it. So any final questions? All right, thank you.
As far as the code that's actually executed, the fourth statement here is essentially the first one. And what this does is it's calling a function. Sorry, the first thing that happens is that the Fibonacci generator is created. So Fibonacci, open parentheses, close parentheses. Oh, thank you. Technology. Fibonacci, the result of that is a generator object. Then it calls this normal function called doublet, passes the generator object in as the sequence parameter to that function, right? And this function returns a generator that operates on the generator that passed in. So this is a new generator object that will give me x times 2 for each x that it gets out of the generator that passed in.
Why does that need to be a sequence?
Well, SEQ is an arbitrary name because it'll work on any sequence type.
Okay, but so is it actually taking a sequence or is it taking a single value?
It's taking an object that it's able to ask for individual items from. So treating an object as a sequence. So this would work with a list, for example. Maybe I shouldn't. Maybe that's a confusing issue.
That's good. That's going to sound horrible, but that looks like a really high correlation, so please be careful where you say.
Oh.
Thank you. Appreciate it.
No, well, it basically takes a generator as input and gives you a generator as output.
It takes any sequence, which includes a generator, as input, and gives a generator because this is a generator here as its output.
Oh, right, because you don't need a generator there. It could be a list.
It could be a list. It could be anything. Anything could be looped over. And then that's it. That's the last time that we call Fibonacci. The last time that we call doublet. The rest of the code is just in a loop where each element in the loop is just getting pulled out of that generator that was returned from doublet. So at the top of the loop, I ask for the first item from this generator. It says, okay, I've got a loop over this thing, which is a generator, which goes up to the Fibonacci generator. Gets the first item, comes back out, multiplies it by 2, gives it back to me.
I guess the part that's confusing me is the Fibonacci generator outputs individual values one at a time.
Every generator outputs individual
Okay,
value.
but so why do we need a sequence when we're only actually dealing with one value at a time?
The name may be confusing. It's anything that can act like a sequence.
But I mean, like, do we have to loop over it because we're only taking one input value?
We could call next on it to get each value, but we still need a loop somewhere to get more than one value.
Okay, but we're calling the object multiple times in the for loop.
We're asking for one item each time through the for loop. So internally, that's calling next, right? So that calls next on this, right? Which ends up feeding it through. So we end up with these 2 stack frames that are still active and partway through processing. And one drives the next to get the next value, and so on.
Correct me if I'm wrong, but objects that can be looped over have a generator inside, right?
No, generator is a special type of so sequences. A sequence is the general way of describing something that you can loop over. I think I'm not getting that wrong. And so a list is a sequence. A dictionary can be treated as a sequence. You just get it in a random order. Lots of collection types can be treated as a sequence. A generator is a very limited one that you can only ask for the next type. You
They
can't.
have some function like that inside that you can overload with one of these. I think I read that somewhere.
Fundamentally, they can be implemented as objects which have special method names that are what's getting called that actually makes this all work. This is sort of the using the language features way of doing it. You can get the same effect by making a class that has sort of turn it inside out, make a class that has methods that you can call. Is that what you mean? Like,
You could define a new style of object, and if you want to make it a kind of object that can be iterated,
yes.
then you define special methods. And
Exactly. So the special methods that you need in that case is only underscore next underscore. So any object that has one of those can be treated like a sequence in this way and looped over.
Including a regular sequence, you could overload inside.
Well, the regular sequence comes with them.
Yeah.
All the regular
you can
sequences have them.
overload it by using the special.
You can change them if you wanted to, yeah. Like that might be something that's done in the case of like an order of dictionary type. So dictionaries, you usually get all the keys back in whatever hash order that they come in. But a lot of people want to remember the order that things got inserted in, so that would be one way of doing it.
You can actually do much weirder stuff like we were developing something where time is discrete.
Yeah.
So you're thinking all over the place. You're thinking of a function that takes you from one instant to the next. You can implement it like that.
Absolutely, yeah. I use it, sometimes I need to consume these things individually. In that case, so I might use the lower level, like calling next on individual items. And I do treat things where I just need to treat, you might as well use what's defined in the language, because then you can use instructions that are there. You can just loop over it for loop, or you can treat it the way you want. There's actually, if you like functional stuff, the func tools module has a whole ton of, all implemented in C, common functional stuff, like things that will work on iterators, but call operators in C so they'll be fast, to combine them, to zip them, or to, I'm not doing justice, but if you like that style of programming, there's a whole bunch of tools for you there if you look at it.
So, I don't speak object-oriented, but I'm just wondering, why doesn't that say return seek times 2 in parentheses instead of for x and seek? Why doesn't seek replace x with seek? SEQ. Return seek times 2, that's it. Why does it say for x and seek?
Because multiplying, so if sequence was a list, multiplying a list means actually taking its contents and doubling it like that. Okay. So that already means something else. So it doesn't mean apply it to each item of. Like the way of saying in Python, I want to apply something to every item of something else is with one of these, with for.
But double it only needs one item for Fibonacci when that generator only needs, every time it's used, only needs one item. Why doesn't it mean, if we replace this instead of saying return x times 2, instead return Fibonacci in parentheses times 2, what would it do?
Well, you'd be multiplying the generator, which doesn't have anything, you get an error. You could ask it for the first off, you could say next, you could create this generator, say next on it, get one item.
So
and then
next Fibonacci times 2.
Yeah, and then you return that. So then double it would be just returning an integer, right? And an integer is not something that you can loop over, so this loop would give an error.
So even though it's in parentheses as a generator, it's still considered like parentheses Fibonacci times 2 over, or sorry, parentheses next Fibonacci times 2 parentheses as a generator.
Well, that's the thing that makes a generator is the for in. Oh, sorry, the thing that makes a generator expression is the for in. If you're making a generator function, it's the yield statement that makes a generator function.
This is like
It's just shorthand.
in mathematics notation. That's where they took it from, where you define a set by set. take the elements in some of the set and operate on them like this, and whatever you get. Right.
Yes, Python is heavily influenced by the mathematics community. That's probably one of the reasons that 1 divided by 2 is now equal to 0.5. It was the main reason given, well, you notice that imaginary numbers are in the basic language. And also, it was the main reason given for Python not being case insensitive. Because people who do math use different letters, different case letters for many different things. But yes, they borrow heavily from that. They borrow heavily from all over the place. They kind of go halfway into a whole bunch of different paradigms from a bunch of other languages, but not so far to be completely consumed with their way of thinking. Is that right?
So a generator expression has to be something you can ask for multiple values from. Is that the idea?
It's shorthand for an object that you can ask multiple values.
So that's why you need the 4x in there.
Yeah.
Basically, you can think of it as something that is a loop over.
So even though Fibonacci is itself something that you can ask multiple values from, putting Fibonacci into an expression doesn't make that expression something you can ask multiple values from. You still
Exactly. It's just an object. It's just another thing.
You still need the 4x to make that happen.
How do you distinguish, if you put the parentheses, aren't you evaluating over Fibonacci?
So the weird, it's slightly subtle syntax. It looks kind of like a function, but it's not a function because it's got a yield in it. And the result of that is that calling a function is what actually creates the generator. Because you've got to remember, each of these things has a call stack, so it's partway through. It has all its own local variables. So the act of calling this function is what creates one of those for you. Right? So if you took that and passed it to somebody else, it would still have the same state that it had the last time you were playing with it. But if you called this thing again, you would get a new one with its own local variables and its own local state.
But what I'm asking is, can you refer to Fibonacci without the parentheses?
Well, in that case, you're just referring to, I guess it's a function. Oh, I can't copy that.
And the point of my question is kind of because
Restructured text is a bit like pandoc, is that right?
A bit like what?
Pandoc form?
I don't know. Okay.
Looks like.
Yes, it's a function. So it is a function that returns a generator.
it's a function. Oh,
Yeah. To me, it looks like yield is a return, except for instead of returning a value, it's returning the state of the function until that point.
No, the state stays in the object.
Well, sure, but it's preserving the state and returning something that contains the state.
No, it's only returning what's on the side of the yield. So in this case, it's just returning an integer.
It's not returning the integer.
Oh, sorry, not returning.
The
It's
first time around, it's not returning the integer. This that function that you just pasted in there, it could say that the first time it's called with the global variable check, the first time it's called, it could return 1, and then the subsequent time, it could return a generator. Right? So it's not that the parser looks at it, finds the yield.
Functions only, I mean, technically they only ever return one thing, but that thing might be a
Well,
different thing.
I could write super function. The first time returned 1, and the second time it had a yield in its code path.
Oh.
And at which point it returns a generator.
No, any function that has a yield in it makes the whole function a generator function.
Sure.
Yes.
Can you do it?
What do you want to put in a return before?
Well, as the first line, do if true, return 1.
Sure.
And then call it and see what it returns.
true, just return one.
So the code, the text itself will still have yield in it, but it will never be reached.
Something like that.
I'm sorry, I can't read it.
Oh.
Yeah, it's the light on the left-hand side of the screen that
Oh. All right. So it's something wrong with return. Oh, okay. So if you're not allowed to do if you return anything that conflicts with it being generated.
So you can just
return
return.
and based on parameters, basically passed into the function, so it wouldn't know.
The parser picks that keyword out and makes the determination.
Right. Okay. So you can have a return and the yield at the same time.
And well, return. You can have a return that returns nothing. What that means is the generator's done. But you still get a generator back.
What happens if you're calling this thing and you come to the return, but you're expecting a value, so
You get a stop stop iteration exception. So if you're in a for loop, that results in ending the for loop, right? If the expression is on the right side of the for loop, then that means the for loop ends. But if you're just calling next on it, then you have to handle that stop iteration